Good morning, guys. I go by the name Ajoku Muhammad Jr., College of Engineering Computer Theory. In today's control system, we have this question. Determine the value of A such that the damping ratio is zero point 0.5. Also, obtain the values of the rise time, peak time, maximum overshoot, and the settling time in its step response. But we'll further proceed by defining some terms as it is in engineering. First, the rise time. Rise time is the time required for the response to go from 10% to 90% of its final value. Time is the time required to reach the very first or highest peak of the response as it is here. Maximum overshoot is how the system shoots past its target, expressed as a percentage. Too much overshoot can damage sensitive hardware. Settling time is the time it takes for the oscillation to finally die down and stay within a small range of the final value. I'm handing it over to my colleague now to start with the derivation and lead us through the calculation.
I'm Jessica Freeman, a third year computer engineering student. So to continue with this question, you have to find the transfer function of this circuit. And checking this circuit, realize that it has a negative feedback. And the formula for finding the transfer function of a circuit with a negative feedback is C of S over R of S. That's the transfer function, or should I say the gain. It's equal to G over 1 plus G times H. And in this case, G, which is the forward part, is 16 over S, open bracket, S plus 0.8, close bracket. And fortunately for us, the circuit has already been represented in the Laplace form, so it makes things way easier. The H, which is a negative feedback, you realize that there's a negative sign here, so it makes it a negative feedback, is 1 plus AS. And putting these into the equation, you get this 316 over this, then 1 plus this times this. So you simplify the equation and you get this, and realize that you finally have the Laplace expression for this whole circuit. That is the transfer function, because Laplace expression of the outputs over the inputs will give you the transfer function of the circuits.
Hello, please. My name is Papa Gujopi Graham, and I'm continuing from where my course mates ended. So here I find the value of omega n. So the transfer function of the second order system is omega n squared over s squared plus 2 zeta omega ns plus omega n squared, where omega stands for the undamped frequency. So we are comparing the numerator with the transfer function in figure 3.14. So here omega n, which is the undamped frequency, omega n squared, which is the undamped frequency, is equal to 16. So then it becomes the root of 16, and then you get omega n, which is the undamped frequency, to 1 rad per second. Thank you very much.
So my name is Samuela, and I'll continue from where my colleague ended. So right now we are to find the value of A. The transfer function of the second order is omega n squared all over s squared plus 2 zeta omega ns plus omega squared n. This is our transfer function of a second system order formula. So to find A, we would compare the denominator with our transfer function in figure 3.1, as my colleague said. So comparing 2 zeta omega n is equal to 0.8 plus 16a. So making us get our equation 2. Dividing both sides by 2, we arrive at zeta omega n is equal to 0.4 plus 8a. Now we substitute the values of zeta and omega n in the question, which is 0.5 times 4, which is equal to 0.4 plus 8a, making us get the value of a to be equal to 0.8. From here, we substitute our value into our equation substitute the value of A in the transfer function, we derive the equation C of S over R of S is equal to 16 over S squared plus 4 of S plus 16. Reminder, every transfer function for second order has a denominator of S squared. Thank you.
Hello, we have to find the rise time of this function, and before that, we have to define what rise time is. So, rise time is the time it takes for a signal to increase from a lower value to a higher value, usually measured from 10% to 90% of the final value. So, given this is the formula given to find the rise time of a second order system, which is pi minus theta over omega d. So, omega d is the damped natural frequency, and the formula is given to this. So we have to find omega d first using omega n calculated in the previous slides. So omega d, substituting the values into it, we have the damping ratio to be 0.5 and omega n to be 4 rad per second. So substituting it into the equation, we're going to get omega d to be 3.46 rad per second. Now we come to the phase angle. The phase angle is giving us tan inverse of square root of 1 minus the damping ratio squared, that's the zeta. So square root of 1 minus zeta squared all over zeta. And we are going to have, also you have to substitute the values into it, which is the zeta, the damping ratio given to you as 0.5. So after substituting it inside, you're going to get the phase angular to be pi over 3. Mind you, we said the formula for finding the rise time of a second order is given as TR is equal to pi minus theta over omega d. So substituting that one into the formula, we are going to get the rising time to be 0.605 seconds. Also, here is a simulation. Here is a simulation of the rise time using a Python. Mind you, we had the same answer with the simulation of the Python as we calculated in the previous slides. So the rise time over here is giving us 0.419 seconds. Thank you.
Hello, I'm Michael, and I'll be taking you through how to solve the peak time for the system. The peak time is the time required for the response to reach its first peak, and it is given by pi over the damped natural frequency. The damped natural frequency is also given by the undamped times the root of 1 minus zeta squared. And substituting in the values for the damped natural frequency, we had 4 times the root of 1 minus 0.5 squared, and we had 0.46 radian per second for the damped natural frequency. So now, knowing the value for the damped natural frequency, we calculate for the peak time, which is pi over 0.46, and the peak time is equal to 0.907 seconds. And this is how we find the peak time, which is the formula of now running Python simulation for the peak time of the system. We also had 0.907 seconds for the peak time. So that's it. Thank you.
My name is Zipporah Apiakubi, and at this stage, we are finding the maximum overshoot. So you may ask what maximum overshoot means. In a control system, especially a second order one, when we apply a step input, the output goes beyond the steady state temporarily, and that amount of response that it goes above is known as the maximum overshoot. Mathematically, it's given as the exponential of negative zeta pi out of 1 minus zeta squared, all in the square root, multiplied by 100%. We substitute the values we've already gotten for our damping ratio and substitute it into the formula. This gives us 0.16 times 100, giving us a maximum overshoot of 16.31%. We will demonstrate this. In our video here. So from here, we can see that it overshoots by 16.3% at this level and settles back here. Thank you.
Hello, my name is Boachi Adumifakofi and I'll be presenting on the settling time. So the settling time is simply the time taken for the output to remain within a specific given error band, and it is usually between 2 and 5 seconds. And so in finding the settling time, which is the T of S, the formula is equal to 4 over zeta omega n. And in our calculation, we found zeta to be 0.5 and omega to be 4. And so our final settling time T of S was equal to 2 seconds. And when we did our Python simulation, we had the settling time to be 2.03 seconds as shown from this simulation. Thank you.
Hi, my name is Obi Manuela Nanaya Japoman. Okay, so thank you for watching our presentation. We explored on control system analysis. We explored the system's characteristics, calculated rise time, peak time, settling time, maximum overshoot, and demonstrated the behavior using Python simulations. From our analysis and simulations, we can see how these parameters affect the system's stability and design and predict system behavior effectively. And we hope this presentation has given you a clear understanding of control system dynamics. Thank you for your time, and we look forward to any questions or discussions you may have. Bye bye.